Okay, question 4. 28 millihenry inductor has a resistance of 22 ohm, connected in series with a variable capacitor and a 24 volt RMS variable supply frequency supply voltage Vs. Frequency of the supply is set at 50 Hz and an ammeter measures the current in the circuit. So let's have a look at this. Here it is, we've got our voltage source, and at the moment it is 50 Hz, but it's variable frequency, so that could change, and it's set at 24 volts RMS, and the current in the circuit is 0.8 amp. And here it is, we've got our inductor with internal resistance. Of course, it's a conductor, so it will have resistance, and see we've got a beautiful dotted line, a dotted rectangle around it to show that this itself is the inductor, and we've got our variable capacitor over there as well, so we can change that. Remember, variable capacitor, usually we've got plates which slide apart, so normally we're changing the area between the plates and our capacitor. Okay, so show that the impedance of the circuit is 30 ohms, so it's a show me, so that indicates that we're going to need to use that value soon, but we've got to show working. So let's have a look at our equation for impedance of a circuit. We've got this here. We've got the voltage, the supply voltage is equal to the current times the impedance Z in ohms. So it's the AC equivalent of Ohm's law. So let's have a look at that. We've got V equals IZ, and we want to find the impedance, so let's rearrange that. We've got impedance is equal to voltage over current equals 24 volt, and we were given the current of 0.8, so that gives us impedance of 30, and of course it's impedance, so it's ohms. Show that the reactance of the pure inductance is 8.8 ohm. Again, let's check our formula for that. The reactance of an inductor, 2 pi FL, so our inductive reactance is equal to 2 times pi times 50 Hertz times 28 millihenry, which equals 8.7965 ohm, but again, two significant figures, so let's call that 8.8 ohm. Later on, if we have to use this value, we will come back to using this rather than that, so it will increase the accuracy of the questions further down. Okay, part C, calculate the total reactance of the circuit. Okay, so in order to do that, we're going to look at a phasor diagram, so we'll have a look down here. Now remember, when we are talking about reactance, impedance and resistance in an AC circuit, we think of this. We think the inductive reactance leads the resistance, which leads the capacitive reactance by 90 degrees each time. So we can combine these to find the impedance. The impedance is the total of the reactances, the two reactances, plus the resistance. So we've already worked out that the total impedance in this circuit is 30 ohm, and so that's our impedance Z. We're given that the resistance is equal to 22 ohm, So impedance is 30 ohm. We're given that the resistance is equal to 22 ohms, and we showed that the inductive reactance is equal to 8.8 ohm. So how do we put this together in this diagram? In the capacitive reactance, we don't know what that is. So let's put in our diagram what we know so far. We know that the inductive reactance is equal to 8.8 ohm, and the resistance is 22 ohm, and the resultant is 30 ohm. And we're asked to find the total reactance. So the total reactance will be the sum of XL plus XC. Now let's have a look. Let's draw a diagram and include, we have the resistance phasor here. Let's draw in, now we don't know whether XC is bigger or smaller than the XL. So let's for a moment imagine that XL is larger, and let's then, the resultant, the supply voltage would be on this side between the inductive reactance and the resistor. So let's have a look then. We know that resultant is 30. So that's the impedance of 30 ohm, and resistance is 20 ohm. So we can find this difference here. And this difference here has got to be the difference between the inductive reactance and the capacitive reactance. Because if we have XL up here and XC down there, we'll subtract this from this and we'll end up with this, XL minus XC with resistance, and that would be our impedance Z. So let's have a look then at this amount here using Pythagoras. We can calculate this. XL minus XC is equal to square root 30 squared minus 22 squared, which equals 20.39. So two significant figures, let's call that 20 ohm. So we're going to say the difference between XL and XC is equal to 20 ohm. Given that XL is equal to 8.8 ohm minus XC, that will give us XC is equal to 28.8 or 29 ohm. So this shows us that the overall reactance is capacitive. So we made a guess earlier on that the impedance was leading the resistance, but actually the opposite's true. So let's draw a better diagram of this. We've got the inductive reactance to be 8.8 ohm, and we've got the capacitive reactance to be 29 ohm, in resistance of 30 ohm. Sorry about that. Resistance of 22 ohm. So now we'll be able to say 29 minus 9 is about 20 ohm, and this then is the impedance here, impedance Z, which we worked out what that was at the very beginning as 30 ohm. So we worked out the reactance of the capacitor as 29 ohm, and now we need to calculate the capacitance of the capacitor. So let's then have a look at our equations then. Here's our equation here, which we're going to use. Capacitive reactance 1 over 2 pi Fc. So calculate the capacitor. We've got Xc is equal to 1 over 2 pi Fc. Rearrange that so that we'll have capacitance equals 1 over 2 pi F capacitive reactance equals 1 over 2 pi frequency of 15 times capacitive reactance is 29, and that should give us a capacitor of capacitance equals, I worked it out to be something like this, 0.0001234, which is equal to 1.1 times 10 to the negative 4. And we can write, because that's the way people write capacitance, we could write that as 110 microfarad. And again, two significant figures. And calculate the phase difference. Let's have a look at our diagram here for phase difference. We've got our diagram down here. Phase difference, we want this phase difference here, this angle theta here, and we can say tan of theta is equal to opposite side 20 divided by the adjacent side 22. We'll rewrite that tan to negative 1 of 20 over 22 is equal to theta. Therefore, theta is equal to 43 degrees, and we will say 43 degrees lagging behind the current through the resistor. So 43 degrees, phase difference between the current. Remember, the current is in phase with the voltage across the resistor, and the supply, that's the Vs, so that's the difference between the resistance, the phase angle between the resistance and the impedance. Okay, H, the capacitance of the capacitor is increased. Explain what happens to the phase difference. Okay, let's check our formula again. Our capacitance, as capacitance increases, reactance decreases. So the capacitance is increased, so that means the reactance decreases. So increase of capacitance decreases the capacitive reactance. So let's have a look at our graph then. I meant phasor diagram. Let's have a look at this. As the frequency increases, as the capacitance increases, our reactance decreases. So we started out with this reactance, and this reactance will get smaller. Maybe come down to here. So what then of our overall? So our overall impedance is this, and we can see this angle is smaller angle. So that was increased capacitance decreases the capacitive reactance, and that decreases the phase angle. The phase angle. There. Okay. With the capacitor, capacitance reset to its original value, the frequency of the supply is gradually increased up to a very high frequency. Explain what happens to the total reactance in the circuit when the frequency first starts to be increased, and then what will happen as the frequency is increased further. Okay, so what happens to the capacitive reactance as the frequency increases? As the frequency increases, the capacitive reactance decreases, and the inductive reactance, as the frequency increases, the inductive reactance increases. So we might start out with this here, XL and XC, and our resistance. Now resistance of course doesn't change at all, so we're concerned with the total reactance in the circuit. So initially the capacitive reactance decreases and the inductive reactance increased. So initially the reactance, the total reactance, will tend towards zero, to tend towards resonance, because when it reaches that resonance frequency, the capacitive reactance will equal the inductive reactance, and they'll cancel one another out, leaving only resistance. And as the frequency then increases further, then the inductive reactance will increase and the capacitive reactance will decrease even further. Okay, so overall the total reactance will increase as that frequency increases very greatly. Next questions are going to be on resonance.